In Egypt, the land of the pyramids, investigators unearth clues to a story far more ancient than the legends of mummies and pharaohs. They reveal a 40-million-year-old ocean monster, Basilosaurus.
Basilosaurus was the largest animal in the ancient seas. The kind of animal that you wouldn't like to swim next to.
This 5.5-ton prehistoric whale terrorized the oceans for millions of years. Where did it come from? And how is it related to its modern counterparts?
Building family trees, tracing the ancestry and the evolution of whales allows us to tell this story of how whales transformed.
Now, new discoveries from this desert plain are unlocking these mysteries. Investigators uncover lost species and the remains of half-eaten prey that reveal the origins of this great hunter.
It's a really, really big animal with really big, powerful teeth. Kind of reminds me of Jaws, only worse.
To decode the secrets of Basilosaurus, we will see this lost beast like never before, flying inside skin and bone. We'll resurrect its vanished world and reveal how Basilosaurus came to rule the oceans. First light in Egypt's western desert. Investigators are on their way to a mysterious dig site known as Wadi al-Hitan. Egyptian paleontologist Dr. Hesham Salam leads the research here.
Wadi Hitan is a very special place. It's a really amazing site.
For hundreds of years, archaeologists have been uncovering the extraordinary treasures left behind by Egypt's ancient civilizations. But this unworldly place has an even richer past, one that goes back not thousands, but millions of years.
This is one of the richest fossil area in the world. So basically all of these layers contain fossils. This is a lot of fun, a lot of excitement, a lot of fossils, a lot of prehistoric life.
Hesham has just established Egypt's very first school of paleontology. Along with a new generation of Egyptian researchers, he's starting to build a picture of the country's prehistoric past.
We have been unearthing amazing stuff from here. One of the most important discoveries so far for my team was a plant-eater dinosaur that lived here in Egypt 70 million years ago.
Beneath Egypt's shifting sands, Hesham and his team are discovering evidence of a time when dinosaurs once dominated this land. But at Wadi al-Hitan, in deposits formed 26 million years after the dinosaurs went extinct, lie the remains of a truly mysterious beast.
This was a really huge animal, lived here in Wadi Hitan long time ago, which is kind of like 18 meters long, is starting from the tip of the nose till the tip of the tail.
Investigators first discovered the remains of this enormous animal in 1832. It was unlike anything they'd ever seen.
At the beginning, they thought that's kind of like a weird lizard. This is why they gave it Saurus, the Greek name for lizard.
The discoverers named the beast Basilosaurus, meaning king lizard. To find out if this really was a lizard, Hesham takes a closer look at the teeth.
You can see right here, amazing, beautiful set of really ferocious teeth. And you can see a really beautiful serration, which is perfect for cutting through the flesh.
The crucial clue is in the roots of these fearsome teeth. Most reptiles, like lizards, have only one root per tooth, but this beast has two.
This is double-rooted. This is one root, another root, and this is one single tooth right here. They're really different. Definitely Basilosaurus wasn't a reptile because it has actually double-rooted teeth.
So what kind of animal is this? Hesham looks for clues in Basilosaurus's vertebra. At first glance, they are unlike those of any other creature.
What makes Basilosaurus special that he has really long vertebrae comparing to the width. This is unique for the Basilosaurus.
Lifting up Basilosaurus's bones from the desert reveals an animal that resembles a mythical beast. 67 gigantic vertebrae form a monstrous snake-like body longer than a train carriage. But the arches on the vertebra are nothing like those of a serpent. They look more like those of a mammal, one that lived in water. Basilosaurus was really a prehistoric whale, the largest marine animal of its day. So why were its bones buried in the middle of a desert, more than 100 miles from the nearest sea? Hesham thinks clues to Basilosaurus's past could lie in the area's unusual rock formations. Wadi al-Hitan is dominated by spectacular sandstone cliffs, known as escarpments, which are constantly eroded by the wind.
Well, if you look at these layers on top of each other, it's like a chapter in a book that telling you the history, part of the history of life.
One geological feature stands out from the others.
You can see all of these boulders with strange branches.
There are hundreds of these bizarre outcrops across the landscape, and they reveal that this desert was once a very different place. One not dry and parched, but watery and full of life.
These strange-looking tubes, some people said it's actually mangrove roots, or other people said they might be like a crustacean burrowing, but either way, they have very clear evidence this area was underwater back then in the Basilosaurus time.
Hesham thinks this area was more than just a mangrove swamp.
If you grab a handful of sand from Wadi Hitan floor, you will see shells, bivalves, and even if you look closer, you might see shark teeth. There's a shark tooth right there. You can see it's really beautiful one. That also indicates that here was a big ocean 40 million years ago.
Today, Wadi al-Hitan lies just south of Cairo, more than 100 miles away from the Mediterranean Sea. 40 million years ago, most of Egypt was covered by an ancient ocean called the Tethys Sea. Wadi al-Hitan was beneath the waters of a sheltered coastal bay, the perfect environment for Basilosaurus to thrive. Scientists discovered the first bones at Wadi al-Hitan in 1902. Many more Basilosaurus skeletons have emerged from the desert sands here ever since. Hesham is still finding them today.
Yeah, look at this white-ish thing. This might be something very interesting to see. This is how we actually locate fossils in Wadi Hitan. And if you give it a close look here, this is definitely something. I can see here like 3 different vertebrae of the Basilosaurus, given the size and the elongated shape of the vertebrae. And also, if you look closely, you can see some of the ribs sticking out. And look at this. I think this is the snout, the very tip of the skull. So basically, we have a skeleton here. This is the skull, and the rest of it is actually hidden underneath the sediments.
This newly uncovered skeleton is one of many scattered across the desert. When the wind erodes the sandstone around these skeletons, the remaining fragments are left sitting on the desert floor. What look like broken rocks are actually 40-million-year-old whale fossils.
You can see all of these piles of stones over there. Just one here, and one there, and one over there, maybe one here, over there. They all are the Basilosaurus skeletons, or ancient whale skeletons, fossils. Because there are so many skeletons in that area, they call it Wadi Hitan, which means the Valley of the Whale. It's a very unique place.
Wadi al-Hitan stretches for 200 square kilometers. So far, excavators have discovered the remains of more than 500 Basilosaurus skeletons here. Hesham believes many more are hidden deep within the area's sandstone cliffs. Each of these lines represents a layer of sediment on the bed of the prehistoric sea. The oldest material lies at the bottom and contains many bones. It dates back almost 40 million years.
Most of the Basilosaurus skeletons come from the sandy layer that you can see it here.
Hesham thinks there is also evidence of the beast higher up, in a much younger and less explored layer.
Look at this over there. It seems like a nice Basilosaurus vertebra sticking out from the cliff. This is amazing.
This pristine Basilosaurus vertebra is suspended around 20 meters above the ground.
Given the vertebra of Basilosaurus up there and the skeleton that we just saw in different levels stratigraphically, definitely Basilosaurus was here for millions of years. We just found the tip of the iceberg. There's thousands of skeletons hiding inside this sediment.
Wadi al-Hitan is the biggest ancient whale graveyard on Earth. It attracts scientists from across the world to study its remarkable fossils. One discovery from the site is transforming our understanding of prehistoric whales.
What we're looking at is the Basilosaurus arm. It's typically like human arm, composed of the shoulder blades and the humerus, and this is the radius, and the 5 fingers like us.
Experts think Basilosaurus used its front limbs to help it swim, just as modern whales do. But at its rear, it was a very different beast.
For many years, the scientists thought that Basilosaurus had only 2 front limbs. All of a sudden, they found the Basilosaurus had legs. That was a big deal in science.
Unlike any modern whale, Basilosaurus had external hind limbs. The discovery sends shockwaves through the scientific world. Why did this ancient whale have legs? In his lab at Mansoura University, Hesham has a treasure trove of Basilosaurus fossils, but very few of its hind limbs have ever been found.
The Basilosaurus hind limb are very rare in the fossil history. This is because after Basilosaurus died, the current maybe moved the hind limb away from the body.
Basilosaurus has 2 front limbs sitting just behind the head. Featuring 5 fingers, they form the core of the pectoral fins, which the animal would have used to steer its body through the water. But towards the back of the skeleton, sitting right next to the spine, is a pair of hind limbs. They feature a hinge joint, complete with a protective cap. It looks like these limbs could bend, and possibly function like legs. So is Basilosaurus a walking whale? Hesham works with precise casts of the original fragile bones. He he pieces them back together to build up a picture of how they were once used.
So we have the hind limbs of the Basilosaurus. You can see this femur, it's not well developed. And this is the tibia and fibula and the ankle bone.
Hesham compares Basilosaurus's legs with those of perhaps the most successful walking animal of all.
This is typically the limb of us, of a human being. And if you compare it with the Basilosaurus femur, the thigh bone, you will see it has the same anatomical features, but look at the size of the femur.
The human thigh bone is around 45 centimeters long. The thigh bone of the giant Basilosaurus is only 25 centimeters.
Really surprising to find a really huge animal like Basilosaurus having really tiny limbs.
With such small legs, Basilosaurus can't have been an expert walker. But some modern marine animals, like sea lions, use small, simple hind limbs to carry themselves more crudely across the land. Could Basilosaurus waddle in the same way? The legs of Basilosaurus could bend and extend like humans, which is the first step towards walking. But to lift a body this large off the ground, the pelvis must be directly attached to the massive spinal column. Hesham and his team plan to 3D scan a Basilosaurus pelvis to see if this is the case. They use a technique called photogrammetry.
This kind of imaging will allow us to actually look at in more detail and orient them in different directions, so it would be easily for us to see the different anatomical features.
If Basilosaurus could walk, there should be a socket linking the pelvis to the spinal column, but the scan doesn't show any sign of one.
You cannot see any place for the attachment between the vertebral column and the pelvis right here. So it's totally not attached. This legs is not for walking.
Scans confirmed that Basilosaurus's legs were too weak for walking. They wouldn't have helped it swim either. They were far too small to propel a giant like this through the water. Hesham believes there is only one explanation for these mysterious limbs. They are an evolutionary hangover.
The hind limbs actually play a crucial role in the whale evolution, and it's actually a remnant from the hind limb of the ancient whale.
Basilosaurus may never have walked, but it had ancestors who did. Who were they? Where did this prehistoric whale come from? Basilosaurus' skeleton alone can't reveal the identity of its early ancestors. So comparative anatomist Joy Reidenberg from the Icahn School of Medicine at Mount Sinai investigates modern whales for clues.
It's always really hard to understand what an ancient animal, a fossil, extinct animal may have looked like or behaved like, because obviously we can't watch it. But the next best thing we can do is watch its modern relatives.
Joy is a specialist in whale anatomy. She thinks the way Basilosaurus moved could hold the key to its evolutionary origins.
I've always loved whales, and I think part of what really drew me into whales is how beautiful they are, how graceful they are. They swim through the water with such ease. They're so streamlined.
Joy wants to know if Basilosaurus swam like its modern counterparts. So today she is heading out to sea to observe whales in their natural habitat off the coast of New York.
Gorgeous, gorgeous day to be out in the water. There's a bait ball at 11 o'clock, right between the two channel markers. There's a really good chance of a whale coming up right there in that bait ball. Wow, this is so cool. Whoa, there's a whale spout over there, right there at 4 o'clock.
Joy spots a humpback whale, one of the largest species alive today. She wants to know how its tail compares with Basilosaurus's.
There we go. Get ready for tail, 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 tail. Oh, it was so awesome to see that. That tail was up in the air, and you can identify the whale by that tail. That makes me so happy.
The design of the humpback's tail is key to how modern whales swim.
Whales have tails that are called flukes, and these flukes power an up and down motion, and that's what pushes them forward. This is very different than what you see in fish, where the tail is going from side to side.
To find out if Basilosaurus swam with the same up and down tail motion, scientists looked for signs that it had horizontal tail flukes, like modern whales. But the evidence is difficult to find.
The soft tissues of the tail don't fossilize. And even in modern whales, there's no bones in the tail flukes themselves. And at first, this was a bit of a mystery to us.
A clue is in the spine of Basilosaurus. Along most of its 18-meter length, the vertebrae have flanges sticking out to the side. But the short, flat vertebrae in the tail section have no flanges. Modern whales share this feature. It's where their flukes attach to their bodies. Basilosaurus only had room for a small fluke on its tail. So to propel its 7-ton weight through the water, it would have to move its entire body up and down through the waves. Basilosaurus may not have been as sleek and graceful as a modern whale, but the way it swam reveals that both animals share a common ancestor. Joy examines vertebrae from 3 modern whale species, the humpback, the porpoise, and the dolphin, to discover more about their mysterious relative and how it moved. This spine hides a remarkable feature that originates from the early ancestors of all whales.
What we notice is these spinous processes that are going up this way dorsally are flanked on either side by these projections. The projections are making this type of an interlock. That allows sliding in the up and down direction, but very little movement from side to side. So we can move these vertebrae back and forth this way, but it's very hard to move them, to twist them side to side.
These interlocking vertebrae are crucial for stabilizing the whale's spine as it swims. By preventing side-to-side movement, they allow the spine to flex up and down with maximum efficiency.
You see them in the porpoise, you see them in the dolphin, you see them in the humpback whale. All whales have this. If we could find another animal with similar restrictions on the spinal movements, it would give us another clue as to where the ancestors of whales came from.
Joy thinks these ancestors were completely different to the whales we know today. 400 million years ago, most life was still in the ocean, where it had first developed, and fish swam with a side-to-side motion. Over time, some species left the water and learned to live and walk on land. When they developed into mammals, their spines evolved to move up and down as they ran. Then, about 50 million years ago, a group of deer-like mammals returned to the water. Their hind legs disappeared, and their tails developed flukes for propulsion. But to this day, a whale's spine still moves as if it's galloping, just as their ancestors once did on land.
So why did the whale's ancestors decide to go back into the water? After all the evolutionary effort that went into becoming a land animal and adapting to galloping on the land, why throw that all away and go back to the water? It's a bit of a mystery.
Discoveries from Wadi al-Hitan are helping scientists to work out how Basilosaurus fits into this strange story. Tiny legs found alongside the enormous skeletons are clues that this ocean giant had land-dwelling ancestors. Paleontologist Steve Brusatte from Edinburgh University is an expert on the evolution of mammals.
Building family trees, tracing the ancestry and the evolution of whales allows us to tell this story of how whales transformed.
Steve thinks there's a clue to the origin of Basilosaurus, hidden inside its skull. It resembles that of a crocodile, but double the size. Its nostrils have fused and moved up the head, closer to where modern whales have their blowholes. Its brain probably weighed only 2.5 kilograms, which means it was smaller than the brains of today's whales. And tucked away under the skull, it had a bony shell called the bulla, which contained the inner ear. It bears a striking resemblance to the bulla of a prehistoric land animal found on the other side of the Tethys Sea in Pakistan, called Pakicetus.
Now, Pakicetus, it looked kind of like a wolf. It's an extinct mammal. It's known only from fossils, but it's a very important mammal. In fact, I think it's one of the most important discoveries in all of paleontology over the last several decades.
Outwardly, Pakicetus was a classic land mammal, with 4 strong legs which allowed it to walk on land. But the shape of its bulla links it with Basilosaurus. Steve thinks it shares this feature with other whales too.
The bulla bones of whales are really distinctive. Their bullas are really thick and really robust and really dense, and especially the rims here. And that helps them hear better underwater. Now, what's really intriguing is that we see these thicker bullas with these thick rims in Pakicetus.
Pakicetus's remains predate Basilosaurus by nearly 10 million years. While they were still only around 1.5 meters long, they had begun to develop the distinctive underwater hearing apparatus of a true whale. But did Pakicetus ever go into the water? Steve thinks the answer may lie with a well-known living species.
Hippos are the closest living relatives today of the whales. They probably last shared a common ancestor 55-ish million years ago. And there's some commonalities between the way hippos live today and the way that we think some of the ancestors of whales lived tens of millions of years ago.
Hippos spend up to 16 hours a day submerged in water. Their skulls are specially adapted to help them see above the waterline.
Here is Pakicetus' skull from above, and you can see here are the eyes, and those eyes, they would have been on the top of the skull a little bit so they could peek out. So if this animal was in the water, the eyes could see above the water a little bit, kind of like a crocodile and kind of like this hippo here. And so this was an animal that was at home on land, at home in the water.
Pakicetus fossils are a window into the time when Basilosaurus's ancestors were taking their first steps in the water.
Where you really see its behavior is when you zoom in on the teeth, and here's some of the teeth of Pakicetus. And these teeth are sharp, and they are pitted and scratched. They have all kinds of wear on them from eating food, and not just any food, but eating flesh, eating meat, and it was probably fish that they largely ate. And it was from these sort of behaviors that these mammals went into the water.
Pakicetus entered the water to hunt, kickstarting the process of evolution that led to the rise of a predator like Basilosaurus. But Pakicetus never made it to the open ocean. What attracted later whales to move into deep water? On the outskirts of Wadi al-Hitan, investigators discover astonishing remains that could help answer this question. The bones they unearth here are from a completely new species, which they name Phaeomycetus anubis.
This is Phaeomycetus anubis. We have nearly complete skull. We're just missing a few pieces of the front and the cheekbone. And it's kind of like the shape of a very ancient whale like Pakicetus from Pakistan.
Hashem can figure out how Phaeomycetus anubis fits into the timeline of whale evolution from the age of the deposits it was found in.
Although the Phaeomycetus were found very close to Basilosaurus, it's actually coming from different layer, older layers than Basilosaurus. So it would fit in the middle between Pachycetus and Basilosaurus.
Phaeomycetus anubis could be a missing link in the whale family tree. 50 million years ago, all whales lived inland, in freshwater streams around India and Pakistan. 2 million years later, they first moved into the area's coastal waters. By 43 million years ago, they had crossed the deep ocean, so we now find their remains in Africa and North America. Today, whales have conquered the planet and can be found in all the world's oceans. Why did species like Anubis give up trickling streams for almighty oceans? A clue lies with its fearsome skull.
So all of these gap or hole will fill with the chewing muscles to go through the skull and also attach it to the lower jaw, which make it really deadly bite indeed. We can say Phaeomycetus anubis were preying on turtles and sea cows and large fishes, maybe also other whales.
The early seafaring whales, like Anubis, evolved to eat far larger prey than their freshwater ancestors did. By entering the oceans, they unlocked the world's biggest pantry, paving the way for the likes of Basilosaurus. How did Basilosaurus rise to become the apex predator of the oceans? Among the incredible hoard of fossils found at Wadi al-Hitan is evidence for how Basilosaurus hunted. When paleontologists dug up a Basilosaurus skeleton, they found strange objects that didn't belong to it. Scattered around the area of the stomach were fragments of other animals, possibly part of this whale's last meal. Among them, a 5-meter-long shark, and one of Basilosaurus's close cousins, Dorodon. Both of these animals were apex predators themselves, but they were no match for Basilosaurus, which sat firmly at the top of the food chain some 40 million years ago. How did Dorodon end up as Basilosaurus's dinner? A typical Dorodon is 5 meters long, with a skull about 2/3 the size of Basilosaurus's. But when Hesham looks closely at the teeth, it's clear that this is not a fully grown Dorodon.
Well, like any other mammals, they are actually replacing the teeth over time. You can definitely see the adult tooth as actually replacing the baby tooth right here. So this is the baby Dorodon still growing and replacing their teeth.
This juvenile Dorodon is part of a strange trend seen across the site.
Here in Wadi Hitan, we find half of the Dorodon specimen are babies. But unfortunately, we didn't find any of the Basilosaurus baby here.
Why are there so many Dorodon young here, and yet no Basilosaurus young? Hesham believes it's a relic of Basilosaurus's brutal hunting strategy.
Based on what we see here in Wadi Hitan, definitely the Dorodon come here just to give birth, and Basilosaurus come to hunt the Dorodon and its baby.
The sheltered bay of Wadi al-Hitan was the perfect place for Dorodon to deliver its offspring. But it was also prime hunting ground for a hungry Basilosaurus who came to feast on the defenseless juveniles. To find out how it tackled its prey, Joy Reidenberg compares Basilosaurus' teeth with those of its modern counterparts.
What we have in front of us here are a whole bunch of teeth from different types of small and large whales. Each of these different types of teeth had different functions. And if you look at the teeth, we get an idea of how they're feeding.
First, she must select the species of modern whale that is the closest comparison.
To the untrained eye, Basilosaurus probably looks a lot like modern-day really big giant whales, such as fin whales, blue whales, humpback whales. But in fact, those whales are very different because what they feed on are very tiny little animals. They don't hunt with teeth in their mouth. They use baleen plates. This, for example, is a baleen plate from a fin whale. And it uses these little hairy brush surfaces to trap prey. Very different from what Basilosaurus was doing.
With the modern giants out of the running, Joy turns towards today's smaller whale species.
If we want to compare Basilosaurus to a modern whale, it would have to be the toothed whales. But if we look at most of the modern toothed whales, they're relatively small, like dolphins. It's not really a very good comparison to Basilosaurus because they're eating very small fish.
Most toothed whales hunt on much smaller prey than Basilosaurus did, but one species is a clear match.
The closest to a Basilosaurus would probably be the killer whale, which is one of the few species of whales that hunt other whales.
The orca, or killer whale, is the apex predator of the modern oceans, capable of killing whales twice its size. Its teeth are its secret weapon.
We're looking at a replica of an orca or killer whale skull. If we look at the shape of orca's teeth, we get an idea of how they're feeding. What they're doing is using these sharp cone-shaped teeth to puncture into the flesh of the whale that they're trying to kill, and they can tear away pieces of that flesh. This is good for grabbing prey and swallowing it whole, like big salmon, for example, or taking a chunk out of a larger animal, like another whale, and then they swallow that chunk whole.
To find out if Basilosaurus did the same, Joy compares its teeth with the orca's.
This is a skull of Basilosaurus, and what we notice is it has 4 different types of teeth in its mouth. That's very different from modern whales, which all have the same kind of teeth. If we look at the shape of the back teeth, we notice that they're very different. They have multiple cusps and they overlap each other, which means that they may have used them for processing their food.
Unlike the orca, Basilosaurus had back teeth that could slice meat into small, easily swallowed pieces. But their front teeth have more in common.
This is an orca tooth, and look at how it's a similar shape. It's cone-shaped with a little bit of curve. This is a tooth for biting and puncturing into prey. Basilosaurus could use its front teeth in the same way that killer whales do use their front teeth to pierce into their prey and bite chunks off.
Basilosaurus could have used its front teeth to tear chunks from its living prey. Further evidence of their hunting techniques comes from a remarkable find. A haul of juvenile Dorodon skulls, dotted with bite marks so deep they would have been deadly. When researchers compared these marks to Basilosaurus teeth, they were a perfect match. It looks like Basilosaurus attacked from the side and chomped down hard to disable the Dorodon before feasting on its flesh. Basilosaurus's ferocious hunting tactics took it to the top of the ocean food chain. But if it was such a skilled hunter, why is there no Basilosaurus swimming around today? Hesham thinks a sudden change in Egypt's landscape could help explain why Basilosaurus disappeared at the end of the Eocene epoch.
At Wadi Hitan, you find the Eocene layers, which is like marine fossils everywhere, whales, sea cows, and turtles, and so on. And all of a sudden, that's changed at one single layer, and all whale fossils disappear from the area exactly at 34 million years ago.
After this time, very different species seem to have inhabited the areas around Wadi al-Hitan. Creatures that lived not in the sea, but on land.
Not far from Wadi Hitan, all of a sudden you find terrestrial mammals, fossils everywhere, starting from different type of ancient elephant, This is one tooth of Meryutherium, the very primitive elephant without any trunk. And sometimes you find bats. This is the lower jaw of a bat.
Hesham thinks one extraordinary discovery is most revealing of all.
One of the most important fossils ever found from Fayoum would be this Egyptopithecus, the Egyptian monkey. This is the cast of it. This is the face. You can see the eyes and the nose, and if you flip it, you can see the teeth. This is very important fossils in the history of human evolution.
Egyptopithecus was less than a meter long, similar to a modern howler monkey. Some scientists believe that it was an ancestor of modern humans. Far from a marine species, this primate lived in a woodland habitat.
Egypt changed from the bottom of the ocean to really green forest, full of really amazing fossils.
What triggered this abrupt change in the landscape? 34 million years ago, Earth begins to cool. As water freezes into ice, sea levels drop. The Tethys Sea retreats from modern Egypt, and Wadi al-Hitan is no longer underwater. Experts believe the sudden shift in climate contributed to Basilosaurus's extinction. In this new world, different whale species emerge.
After the Basilosaurus time, the whale divided in two main groups: the baleen whale, that has no teeth at all, and also the toothed whale.
Modern toothed whales, like dolphins, have built on Basilosaurus's predatory prowess by evolving a remarkable new ability: echolocation. This allows them to navigate and hunt with their ears by detecting the location of nearby objects from reflected sound waves. Basilosaurus couldn't echolocate, but Hesham thinks the shape of its skull shows how this remarkable super skill developed.
The scientists said that's the asymmetrical skull of Basilosaurus that's actually inherited to the modern toothed whale as well.
Basilosaurus's lopsided skull gave it directional hearing underwater, the first step on the path to echolocation. It would take other species millennia to refine this skill. The sophisticated whales that rule today's oceans owe a huge debt to their prehistoric cousin. Egypt's ocean behemoths may now be a thing of the past.
Basilosaurus, probably one of the most impressive fossils that I can think of because of its sheer size.
But their bones are still revealing one of the most incredible evolutionary tales of all.
Basilosaurus records that moment in whale evolution where whales left the land behind and went all in for living in the water.
Paleontologists continue to dig in search of the next piece of this prehistoric puzzle.
Being here in the desert looking for prehistoric life is just amazing. You live in another world. It's really something not many people do, so I'm really lucky to do that.
It's thanks to ancient species like Basilosaurus, the prehistoric colossus, expert swimmer, and fearsome hunter, that we have the majestic ocean giants that we know today.